In the last class, we discussed regarding the introduction to thermal radiation, then what are the properties of surfaces when compared to radiation, the difference between other modes of heat transfer with radiation, then what is a black body, then emissivity, then different types, total hemispherical emissivity, spectral hemispherical emissivity and all. Then we started with laws of black body radiation. So Stefan-Boltzmann law already, that's a fundamental law regarding thermal radiation, already we compared with that conduction and convection fundamental laws. Then in the last class, Planck's distribution we have already seen. In today's class we will see other black body radiation laws. The first we will start with the Wiens displacement law. So we stopped at Planck's distribution. So what is Planck's distribution? Planck's distribution is to find out spectral black body emissive power. That I can write it as Planck's law. E B lambda. So here we have to say that this is spectral. We have to read like this. This is spectral black body emissive power. So this is spectral or it is a monochromatic at a particular wavelength. This B represent black body, spectral black body, and this E, of course, it is emissive power. Emissive power. So this is E B lambda is nothing but spectral black body emissive power. According to Planck's distribution, it is nothing but C1 by lambda raised to 5, C2 by E raised to C2 by lambda t minus 1, e to the exponential of C2 by lambda t minus 1. This C1 and C2 are constants, and this is wavelength in microns. Then here is to, so this is a Planck's distribution. In this Planck's distribution, if I am keeping temperature T as a constant, and if I am drawing EB lambda versus lambda, if I am drawing EB lambda, if I am drawing EB lambda versus lambda, then this is a okay. If I am drawing that, then I can get for a particular temperature. If I am drawing at a particular temperature, suppose that temperature is 300 Kelvin. For 300 Kelvin, I can get a curve like this. Okay, this is a curve for 300 Kelvin. Maybe I can write it as 300 Kelvin. If I am drawing this one, this may be 500 Kelvin. This may be some 2000 Kelvin. This will be some 5000 Kelvin. Okay. Okay. So if we are keeping temperatures, so in this Planck's distribution, if we are keeping temperature as constant, maybe 300, it may be 500. This is 500. This is 2000, and this is 5000 Kelvin. And here at the lower side, it is at a lower temperature, and when it is going up like this. So this graph is EB lambda versus lambda. Okay. Then what are the observations from this particular distribution? The points we can notice. First one, what are the observation we can get? The observation is that as the temperature increases, MC power also increases. That is very fundamental or common thing. Temperature increases, MC power, or I can write it as temperature increases, MC power is on increase. MC power is increasing. As temperature increases, MC power also increasing. Then another thing is that we can get a family of curves, and each curve, it is temperature is reaching to a maximum, then it is decreasing. The distribution reaches a maximum, then decreasing, then decreases. The distribution which reaches a maximum then decreases. The first thing is that as the temperature increases, at higher temperature the EB lambda, so the MC power will be more. Then at lower temperatures the MC power will be less. So that higher temperature MC power is more. Then it reaches a maximum. Each curve, if you are taking each curve, it reaches a maximum, then it is decreasing. Okay, I can mark. So these are the peaks. Maybe I can join this. Okay. When I am joining these peaks, what is observed is, as the temperature goes up, the spectrum shift towards shorter wavelengths. The peak of the spectrum, the peak of the this curve, peak of this curve shifts towards shorter wavelength. Curve shifts towards shorter wavelengths. That is, the peak of these peaks of the family of curves shifts towards shorter wavelength. So here the wavelength is on increase, it is shifting towards shorter wavelength. Here the wavelength will be short. So it is the peak shifts, or we can say that the peak shifts towards left. That is, so these are the observations. As the temperature is increasing, the MC power also increasing. It is reaching the spectrum, or this curve reaches a maximum, then it is decreasing. That is an observation. Then peak of the curve, or the peak, we can draw a line connecting this peak. This is the line connecting the peak of this curves. The peak of the curve shift towards shorter wavelengths. Peak of the curve shift towards shorter wavelengths. In 1893, a German scientist, he coined a law for this, that is known as Wiens Displacement Law. First I will write what is that? That is lambda maximum into a particular temperature is equal to a constant value 2897.6 micrometer Kelvin. Lambda maximum, this is not the maximum value of wavelength, this is the maximum value of the MC power, maximum value of the MC power at a particular wavelength. So this is maximum value of MC power at a particular wavelength into temperature. If we take this case, so this for 300 Kelvin, if I am taking like this is the lambda max for the case of 300 Kelvin. That is lambda max into temperature, that is 300. You will get 2897.6 micrometer Kelvin. This usually we are not writing that much precise. So usually it is taken as 2898 micrometer Kelvin. This quantity usually we will take it as 2898 micrometer Kelvin. This formulation we are calling it as Wiens Displacement Law. Wiens Displacement. This particular formulation we are calling it as Wiens Displacement Law. I will start once. I will just recapitulate. So from Planck's law we already learned. Planck's law is for spectral blackbody MC power. That this is the expression C1 by lambda raised to 5, C2 by e to the power of C2 by lambda t minus 1. In this we are fitting a curve or something like. We are keeping temperature constant. Temperature may be 300, 400, 500, 1000, 2000 or something like that in Kelvin. Then if you are plotting EB lambda versus lambda, this is EB lambda, we are plotting EB lambda versus lambda, EB lambda versus lambda, then we will get a family of curves for 300, 500, 2000 and 5000. This curve we can have certain observations or certain points from this curve. What are that? What are observation we can take? One is temperature increases. Then when the temperature is on increase, then MC power is also increasing. The MC power is also increasing as the temperature increases. The another point is that all the curves at a particular temperature, it reaches a maximum, then it is decreasing. It reaches a maximum, then it decreases. Then peak of the curve. Here, peak of this curve, that is all these points, we can draw a line, we can draw a locus of all these points. The peak of this curve shifts towards shorter wavelength. Here the wavelength is shorter and this peak is shifts towards shorter wavelengths. So in 1893, German scientist, he is Wiens, he formulated lambda maximum into T is 2897.6 micrometer Kelvin. So we usually take it as 2898 micrometer Kelvin. Okay, so these are the this is Wiens displacement law. Already we learned Stefan Boltzmann. We already learned Planck's distribution, Stefan Boltzmann law. Then this Wiens distribution. So almost 3 laws on blackbody radiation we have discussed. Then some more insights on this particular Wiens displacement law. What is the significance? If I am taking room temperature if I can take it as some 300 Kelvin. If I am considering this room temperature as some 300 Kelvin, then lambda, so that is, this is not lambda max, it's not maximum value of wavelength, it is the value of wavelength at which MC power is maximum. Lambda max into, so T I am taking as 300 Kelvin, that is equal to 2898. Then how much is the lambda max? So lambda max is coming nothing but 2898 by 300. It will be coming roughly 9.66. Okay. So lambda max, that is in microns. This 9.66. If the temperature is 300 and this 9.66, you know that from the electromagnetic spectrum it is coming in the IR region. It is coming in the IR region. So this is not coming in the visible region. Then what will be there in the visible region? So we already know that for radiation, the sun's energy, so we can see light and all, because from solar radiation it is coming, and usually the average temperature of the sun, we are taking it as 5800 Kelvin. So if you are doing this calculation for sun's temperature, this is nothing but 5800 Kelvin. Okay, Kelvin, that is not required. Then lambda maximum 5800. So you will get roughly it is 0.5 microns. you will, as we are getting it's 0.5 microns in the visible range, we can see that our visible range is from some 0.4 microns to maybe some 0.76 microns or 0.7 microns. That is the visible range. As it comes in the visible range, most of the we can see the light. Why? Because of this particular thing, because according to Wiens displacement law, maximum value of emissive power for a particular wavelength into temperature is 2898. That value is constant. If it this is K and this is in microns. Okay, so this I think some more idea you got from this Wiens displacement law. If we know the temperature, at what temperature this particular radiation is happening, then we are in a position to find out the wavelength at which maximum value of MC power is occurring. Now Stefan Boltzmann law, Planck's distribution and Wiens displacement law is over. Then using this distribution, if I am another insight what we can get from this law is, or generally if I am drawing like this, okay, if I am drawing what is this one? It is nothing but this is spectral. It is not spectral. This is Blackbody MC power area under this curve. How we are getting that? That is EB is nothing but 0 to infinity EB lambda d lambda. If I am getting 0 to infinity EB lambda d lambda, then I will be able to get EB, that is Blackbody MC power. We have to integrate over 0 to this is infinity for all wavelength. Then we are getting the value of this is also possible with that. There is no point in this lambda max. Often we are not interested in getting this MC power of Blackbody, because we have to integrate from 0 to infinity. Suppose for 0 to a particular wavelength, if I want to find out the MC power, I want to find out MC power of a particular wavelength. Okay, what is that particular wavelength? Maybe if I want to find out MC power until this point lambda 1, or if I want to find out MC power, or if I want to find an MC power in this band from lambda 2. So this way we can call it as band emission. Okay, so in the particular band, in certain practical cases, usually we are encountering to find out how much is the energy, that is MC power associated with this particular wavelength band. For that we have some more formulation. So now what is this F lambda, that is Blackbody radiation function? I already told you that we are not always interested to find out what is the MC power from 0 to infinity, but maybe the MC power from 0 to lambda or 0 to at a particular wavelength. Okay, then what is this F lambda? F lambda is the Blackbody radiation function, and this is the fraction, that is the fraction of radiation emitted by a Blackbody at a particular temperature in the wavelength band. So the band emission means we have to find out the fraction of radiation emitted by a Blackbody at a particular temperature. The temperature may be 3000 Kelvin, 5000 Kelvin, 2500 Kelvin, something like that, in the wavelength band. So I already told you, always it is not from 0 to infinity we are interested, but in a particular wavelength band, maybe some 0.8 microns to some 3 microns. How much is the band emission? So that how much is the radiation emitted? So that sometimes we have to find out in particular application. So we will work out a problem based on that, then the idea will be more clear. Okay. Then F suffix lambda, that we are calling it as Blackbody radiation function. What is this one? F lambda 1 to lambda. This lambda 1 can be maybe some 0.5 microns. This lambda 2, that can maybe some 3 microns, something like that. Then what is this one? This is F 0 to lambda 2, that is 0 to 3 microns minus F of 0 to 0.5, if I am considering it as 0.5. Then where I will get all this F 0 lambda 2 and all these values? How can I find out? This we can find out from by integrating our Planck's law and all. We can put that value and all we can find out. But in your data book or tables are available by which you can get. So there is a chart called Blackbody radiation function chart that is available in your data book, as well as in the textbook also it is available. So people have already found out and they have recorded how much is the fraction of radiant energy emitted by a black surface. So Blackbody radiation function chart for a lambda t, so a particular lambda is given, then we have to multiply that value with the temperature. Sometimes the temperature is given as 300, 500, something like that. Then lambda t, suppose the lambda t is 1000, then this Blackbody radiation function is 0.00321. That means 0.03% is only is radiating. Suppose this value is 1900, then it means that only 5%. So we have to multiply with 100, then only 5% is coming in the that is the fraction of radiation energy is only 5%. So something like that. So this is regarding the Blackbody radiation function. Then these things can be depicted by this. Suppose I am drawing a curve like this, then this is EB lambda, that is spectral Blackbody MC power by the ratio of spectral Blackbody MC power to the Blackbody MC power. Then for a particular, so we are interested, so F of, see you can see that F of lambda 1 minus lambda 2. For example, F of lambda 1, that may be 0.5 minus F of 3, or in that terms I can write it as F of 0.5 to maybe 0.7. This I had to take it as F of 0 to 0.7 minus F of 0 to 0.5. If this is 0.7 and this is 0.5, that is 0 to, we are taking this from 0 to this one, then this is 0 to 0.5, the entire quantity minus this quantity, you will get this band emission. So this for simply for an example. We will do one problem based on that. Okay. The idea is that always we are not interested to find out the fraction of energy leaving, but we may be, in certain cases we have to find out how much is, we have to find out how much is the at a particular wavelength band, how much is the energy is coming, so in between two particular wavelengths. Okay, now we will work out a problem. So the concepts will be more clear by doing that. We can just go through this. The temperature of the filament of an incandescent bulb. So bulb is 2500 Kelvin. The temperature of the incandescent bulb is given as 2000. That filament is 2500 Kelvin. Assuming the filament to be a black body, we are assuming the filament as a black body. Determine the fraction of the radiant energy emitted by the filament. So the same way, already we discussed how to find out the fraction of radiant energy. So lambda t, that value is available in the data book. Then corresponding to that we have to get the fraction of energy. Then we will be able to find out. energy emitted by the filament that falls in the visible range. So visible range, we know that it is from 0.4 to 0.76 microns. Also determine the wavelength. How to find out the wavelength? Also determine the wavelength, that's not wavelength at which the emission radiation from the filament peaks, or the wavelength at which the emission of radiation, at which the emission of radiation from the filament peaks, from the filament peaks. So we have two things. So what is the band emission they are asking, and the next one to find out is how much is the wavelength at which the emission of the radiation from the filament peaks or maximum. So this peak value we can find out from Wiens displacement law, that is lambda max into temperature lambda for a particular MC power, maximum MC power, into temperature, that is 2500, that is equal to 2898 microns Kelvin. That from that we can get this peak value. And the first values, how we can find out? Okay, first we have to find out what is this lambda t. So lambda t value I can so we have to find out. Now the visible range is from 0.4 to 0.76 microns. This I can take it as lambda 1, this is lambda 2. This is for our particular program. This is lambda 2. Okay. Then lambda 1 into t. Lambda 1 t is nothing but 0.4 into 2500. That comes 1000 microns Kelvin. So this value I have written here 1000, corresponding that this we are getting from the data book or the any table which gives the Blackbody radiation function chart. So this 1000 lambda t is not Kelvin, lambda t value, that is microns Kelvin, that value is 0.00321. Okay. Then what is lambda to t? Lambda to t, that value is 0.76 into 2500. That is the temperature that we cannot change, that is 1900 microns Kelvin. Microns Kelvin. Okay. Corresponding to 1900 we have the value 0.053035. Then how to find out this band emission? So now things are more clear. Now what we have to do is, this is nothing but this is 0.4, this is 0.76. Okay. So EB lambda by E lambda, all things are okay. We have to find out. Then this is nothing but, here also we can rewrite, that is lambda 1 is what is lambda 1? Lambda 1 is 0.4 minus 0.76. We are taking from 0 to 0.76, how much? Minus, that is fraction of radiation emitted from 0 to 0.76 minus 0 to 0.4. This we can get it. This lambda 2 is 0.76 minus 0.4. Okay. Then how much is that value? That value is nothing but, we have to so this value minus this value. So that is 0, that is nothing but, that is F, this value is F Okay, we'll do that. We can write it as from F, that is 0.4, 0.76 is equal to F of 0 to 0.76 minus F of minus 0.4. That is nothing but, we already know the value, that is 0.053035 minus 0.321. What you are getting is 0.052714. Okay. So this is the value what we are getting, and from that what we can understand, if I am taking the percentage, that is only 5%, only we have to multiply with 100, so in order to get the percentage, that means only 5% radiation is falling in the visible region. That's why in the incandescent bulb we are replacing, and nowadays the CFL and LED bulbs are coming, because in the incandescent we are using the filament, because that we are considering it as a black surface, black body and all. When we are considering that radiation, only 5% is coming in the visible region. So from from this calculation we can understand only 5% is coming. So that's why we are going for other types of other lights for the lighting purpose. Okay, we are going for CFL and other things. So only 5% and all other are coming in the IR region. Maybe at higher wavelength, it is going in the higher region and all. So that is then in the IR region, if some radiation or something is there, then how can we find out that? We have to use some IR cameras. IR cameras are visible, or with our eye it is insensitive, but IR cameras we can use to detect. That is why detection is in the IR region. We are doing with the IR cameras. Okay. So this is regarding that. This one, yeah. Then the second part. So now we are getting 5%. It is coming. So we can say that only 5% is coming in the fraction of the radiant energy emitted by the filament that falls in the visible range. So in the visible range, only 5% is falling. Then how to find out the second part? The second part is you have to find out to determine the wavelength at which the emission of radiation from the filament peaks. So this is the emission of peaks here. This is the maximum value of emission at a particular wavelength. Then so we have to use lambda max into, so T is equal to, this is Wiens displacement law, that is 2898. Then we can find out lambda max into 2500 Kelvin, that is our temperature, 2898. Therefore lambda max is nothing but 2898 by 2500. We will get roughly as 1.16 microns. So that is then the peak we are getting as the maximum value of emissive power. At the peak we are getting as 1.16 microns. Okay. So two things we have to find out: how much was the fraction which is coming in the visible. It's only 5%. That you can multiply, only 5% is coming. Then another thing is that what is the maximum value of the value of lambda at which emission is maximum. That is nothing but we have Wiens displacement law. When we are using that Wiens displacement law, then lambda max we are getting 2898 by 2500. It is coming roughly 1.16. 1.16 is in the IR region because 0.4 to 0.7, and thermal radiation we are calling it, we are saying that it is from 0.1 to 100 micron. So this 1.16 is falling in the IR region. Now we can study what is the characteristics of radiation incident on a surface. Suppose I am taking a surface, I am considering a surface, and suppose radiation is incident on this. This incident radiation, I can call it as irradiation. That is in watt per meter square. The incident radiation, the total energy which is striking at a particular maybe unit area, if I can take that incident radiation, the term I can use is irradiation, and I can denote it with the term G. Incident is G. So if I am considering this, this is G. Then when it is strikes on a surface, there are three possibilities. Either it can, a part can be, it can be reflected, a part can be reflected, then some can be absorbed, or some is transmitted. Transparent surface, then it can transmit. For opaque surface like metal sheet and all, so like that, then there will be only a reflection and absorption. It depends on certain surfaces and bodies. Anyway, the incident radiation, but a particular unit area if I are taking, I can call the term irradiation. That I am representing it as G. Then this reflected, if I am representing it as GR, this reflected, absorbed is GA, and transmitted is, I can write it as G small t. Okay, if I am in a analogous manner, if I am taking another this thing, if irradiation is 100, then this reflection it may be some 70, then absorption maybe some 20 percentage, and transmission maybe 10%. This is 20% and it is 70%. Suppose irradiation is 100%. If irradiation is 100%, then 70% is gone for reflection, then 20% is for absorption, and 10% that is for transmission. Just as an example. Okay. Then I am considering GR is the reflected, GA is absorbed, and GT is the energy which is transmitted. The term absorptivity T is nothing but alpha is G absorbed by G. Fraction of incident radiation which is absorbed is known as absorptivity. The fraction of incident radiation which is absorbed, that is, which is incident radiation, the absorbed component divided by this. So this is a dimensionless quantity, and the value lies between absorptivity, the value lies between 0 and 1. Okay. Then this is G, so this is absorbed. Then this is absorptivity, this is a part of this one. Reflected, then I can use the term transmitted, I can use the term tau. Then reflected, that is reflectivity. Reflectivity is denoted by rho, that is G reflected by G. Okay. Here also this quantity reflectivity that lies between 0 and 1. Then another term is transmissivity. Transmissivity is nothing but G T divided by G. So that value is also lies between tau, lies between 0 and 1. It is represented, so this absorptivity is represented by alpha, this reflectivity by rho, and transmissivity by tau. All these values we already seen what is emissivity. Emissivity is nothing but mc power of the real surface divided by mc power of the black surface. That value also lies between 0 and 1. Here also absorptivity, reflectivity and transmissivity is the value lies between 0 and 1. And I already told you the incident radiation we can call another term as irradiation. Okay. Then if I am taking or GA plus G absorbed plus G reflected plus G transmitted, that is nothing but G. If I am dividing by G, GA by G plus GR by G plus G transmitted by total or the irradiation. I am dividing by G, so that is 1. That is 1. GA by G is nothing but this is we are defined it as absorptivity plus reflectivity plus transmissivity is equal to 1. This is an important expression we are getting, that is absorptivity plus reflectivity plus transmissivity, it is equal to 1. For a black surface, I am writing some special cases for black surface. By definition, black surface is the surface which allows all incident radiation and it internally absorbs it. When it is allowing all incident radiation, absorptivity alpha is equal to 1. When absorptivity is 1, reflectivity and transmissivity is 0. That is case of a black surface. For an opaque surface, metallic surface if I am taking, it is opaque. Then for opaque surface, transmissivity is 0. That means alpha plus rho is equal to 1. This is a case of an opaque surface. Okay. So for black surface, alpha is 1. Then for an opaque surface, alpha plus rho is equal to 1. Then maybe for white surface, maybe reflectivity that may be 1, something like that. We can define. So depends on the surface, we can have all these quantities. What I was saying is these are radiation incident on a surface. When the radiation, suppose I am taking the irradiation is 100%, then some 70% may be gone for reflection, then some 20% may be absorption and 10% may be transmission. Okay. Then absorptivity is nothing but fraction of incident radiation absorbed, that is GA by G. Its value lies between 0 and 1. This is reflectivity, transmissivity. When I am saying this as absorptivity, it is total hemispherical absorptivity. Alpha, when I am saying that it is total hemispherical absorptivity. Total means for all wavelengths, and hemispherical means for all directions. Similar terms, I can have, if I use this term, this is nothing but spectral hemispherical absorptivity. This is spectral hemispherical absorptivity. Then if I am considering alpha, this is regarding spectral and this is directional. I can write it as, so this is spectral hemispherical, this is spectral hemispherical absorptivity, this is spectral directional, spectral directional absorptivity. This is spectral directional absorptivity. Absorptivity. Similar manner, I can write it total hemispherical reflectivity, total hemispherical transmissivity. That terms also can be spectral hemispherical reflectivity, spectral directional reflectivity. Again, the term spectral total hemispherical transmissivity, spectral hemispherical transmissivity, spectral directional transmissivity. All that terms I can use. Then one more term we have to see is radiosity. In relation to this radiation incident on a surface, the another term we can define is radiosity. Radiosity is usually represented by the term J. So we can see what is radiosity. Radiosity is usually represented by the term J. If I am considering a surface, there is some irradiation. This is G, irradiation. Then this is reflected. It is rho into G is the reflected part, and this is emitted, emission which is happening. So the radiosity J, I can write it as emission plus how much is emitted and how much is reflected. So the total energy leaving the surface per unit area, the total energy which is leaving the surface per unit area, I can call the term radiosity. But today we have learned the term irradiation, that is what all radiation incoming is irradiation. Then what all the energy which is going out, that is which is coming in is radiation, going out is radiosity. So when it is going out means it is reflected plus emitted, that is emitted plus the component of the reflected, and this is emitted, that term is radiosity. Also we learned the terms absorptivity, reflectivity, transmissivity. Then we learned the terms from gray surface and all. So gray surface that is independent on wavelength. So wavelength, the properties are independent on the wavelength. Then so these quantities we already saw. All these quantities we can have total hemispherical, spectral hemispherical, spectral directional, all that. That is a possibility. The one more thing remaining is regarding, there are two types of reflections. Reflections are two types. I am drawing two surfaces. This is an incident ray. It is making an angle here. Then it is another angle. This is a reflector ray. This ray is the incident ray, and this is reflected. If the angle of incident ray with the normal and reflected ray, the normal are almost the same. If theta and phi are same, then this is known as regular or specular reflection. This is known as regular or specular reflection. The angle of incident and angle of reflection are same. Then this is the regular or specular reflection. Then this is the incoming ray, and if it is reflected not at a particular angle, it is reflected all everywhere. So then this is diffuse reflection. Diffuse reflection. So this reflection is known as diffuse reflection. Then in the reflections are of two types. One is a mirror-like, so a very highly polished surface. The angle of incidence and angle of reflection is the same, so theta and phi are the same. This is regular or specular reflection, and if I am considering this is the incident ray, this is the incident ray, and if it is reflected in all directions, I can call it as diffuse reflection. So this is one more term which is remaining in the absorptivity, reflectivity and transmissivity part, that is properties when a radiation is striking on a surface. So reflection can be of two types. So this also we have to get some idea before we going to the next topic. So already we have seen three laws of blackbody radiation. One is Planck's distribution. Planck's distribution, we will get spectral MC power of a black surface, that is MC power at a particular wavelength. Then when we are integrating that spectral MC power from 0 to infinity, when the wavelength is from 0 to infinity, when we are integrating, we will get Stefan-Boltzmann law, that is the MC power of a black surface, that we are writing it as Stefan-Boltzmann constant into T raised to 4 per unit area. Stefan-Boltzmann constant, the value is 5.67 into 10 to the power of -8. So that we already seen. Then from the blackbody Planck's distribution, if we are keeping the temperature constant, then we are drawing, or we are taking the graph of EB lambda versus lambda. We can have a family of curves. There will be a peak, and Wiens says, or Wiens displacement law says, lambda maximum MC power for a particular lambda into the constant temperature, that is equal to a constant value 2898 or 2897.6 microns Kelvin. That is Wiens displacement law. That Wiens displacement law enabled us to find out the wavelength corresponding to a maximum MC power, and we already saw how will be why certain things are seen, where will be the certain things are not seen. So it is coming in maybe sometimes in the IR region, maybe in the UV region, depends on the temperature as well as depends on the temperature of the incoming rays and all. Okay. Then the properties of surfaces, absorptivity, reflectivity, transmissivity, all these properties we have seen. Altogether, this absorptivity, reflectivity and transmissivity, the value when we are adding all that, it is 1. We learned irradiation as well as radiosity. The incoming radiation, we are calling it as irradiation, and the reflector radiation plus emission, that we are calling it as the term J, that is radiosity. Now another important law which connects important law in blackbody radiation is Kirchhoff's law. He found out this Kirchhoff's law. What this Kirchhoff's law says: suppose I am considering an enclosure. This enclosure, I am considering an enclosure here. This enclosure is at a, I can consider this as a, this enclosure is at a temperature T. So this is enclosure is a black, I can consider as a black surface, or it's a radiation coming from a black body. This is having an emissivity, absorptivity, a small object inside. Again, its temperature is T. So a big enclosure that is having a temperature T. So it is a black surface. It's a black surface. Then we have a body here inside. It may not be another body here. It is having values of emissivity and absorptivity. Okay. So it can absorb the radiation which is coming from the black surface here, and also it can emit. Then what is absorb? G absorb. So G absorbed is nothing but into G alpha, the component of irradiation into alpha, that is energy or radiation absorbed by the small body. Energy absorbed by the small body is nothing but G absorbed is alpha G. This I can write it as alpha. G irradiation is nothing but sigma T to the power of 4. Then what is G emitted? That is emissivity into EB. Emissivity into EB. That is E. That is it is not G, it is E. E emitted, that is EB. EB is nothing but sigma T to the power of 4 for a black surface. Then at thermal equilibrium, when we are considering thermal equilibrium, then we can take the surface area also. Then G absorbed, surface area into alpha sigma T to the power of 4 is equal to surface area emissivity sigma T to the power of 4. Then these quantities get cancelled and we will get absorptivity is equal to emissivity. So this at a particular temperature. At a particular temperature we can get absorptivity is equal to emissivity. This is nothing but total hemispherical absorptivity, that is equal to total hemispherical emissivity. We can have so this is for a gray surface. We can consider this for a gray surface. For a diffuse surface, I can write it as alpha lambda is equal to, for a diffuse surface I can write it as, for a spectral quantity, the spectral also, for a diffuse surface I can write it as spectral hemispherical absorptivity is equal to spectral hemispherical emissivity. Spectral hemispherical absorptivity is equal to spectral hemispherical emissivity. So that is another, that also I can write down. Maybe I can write the spectral directional absorptivity and also spectral directional absorptivity is equal to spectral directional emissivity. In that time, it depends on the surface whether it is gray, whether it is diffuse, depends on that, or gray diffuse. We can write all that. So for a gray surface, we can write this. For a diffuse surface or spectral, when we are writing in terms of spectral quantities, for a particular wavelength, then this absorptivity for a particular wavelength, and this is also for a particular wavelength we can find out. What is the significance of this expression? Because if we have for opaque surface alpha plus rho, that is absorptivity plus reflectivity is 1. Then here from this term I can say that absorptivity is equal to emissivity. By knowing only one quantity, then absorptivity is nothing but, from here I can write it as absorptivity is nothing but 1 minus rho. So by finding only one quantity we can find out another quantities. By observing only one quantity, only by knowing one quantity for opaque surface and all, we are in a position to find out other quantities also. Okay, the expression we will we can once again see that is Pitstops law. The Pitstops law is the total hemispherical emissivity of a surface at a temperature T is equal to its total hemispherical absorptivity for radiation coming from a black body at the same temperature. So all that things we already seen. So how it can be derived? It's not a we are considering a black surface, big black enclosure, and we are considering a small body inside that. It is having the capacity for absorption. It is we can write it as G absorption here, emission. So emission is there, absorption it can emit, it can absorb. So it can absorb from the radiation which is coming from the enclosure, then it can emit also. If I am considering that small object, energy absorbed by the object is alpha into G, which is the total irradiation or irradiation. That alpha sigma T raised to 4. Emitted is emissivity into EB. So E by EB is emissivity. So emitted, the radiation which is emitted is emissivity into EB. Emissivity sigma T raised to 4. Then as absorptivity sigma T raised to 4. This way at thermal equilibrium. Thermal equilibrium we can equate like this at a particular T. Then total hemispherical absorptivity is equal to total hemispherical emissivity. For a spectral quantities, for a gray surface, for a diffuse surface, we can have a spectral absorptivity. Spectral hemispherical absorptivity is spectral hemispherical emissivity. The significance is that for opaque surface and all, alpha plus rho is equal to 1. Then from this one, total hemispherical absorptivity is equal to total hemispherical emissivity. Then by knowing only one quantity, we will be able to find out all other quantities for an opaque surface. Emissivity, maybe we can find, if we know the value of emissivity, we can find out absorptivity or reflectivity, all that we will be able to find out. So this is the significance of this particular Kirchhoff's law.